Ok, chào cả lớp nha. Nay chúng ta tiếp tục các cái buổi bảo vệ bài tập lớn đúng không? Hôm trước thì chúng ta đã có nhóm số 2, số 3 và số 4 trình bày rồi. Thì buổi ngày hôm nay thì chúng ta sẽ tiếp theo bằng các nhóm số 5, 6, 7, 8. Về mặt thứ tự thì do cả lớp chúng ta thống nhất thôi. Nếu không có nhóm nào có ý kiến thì chúng ta sẽ tiếp tục với nhóm số 1 đi. Nhóm số 1 hình như là chưa báo cáo. Nhóm số 1 có đồng ý không nhỉ? Cả lớp có đồng ý không? Không chúng ta sẽ bắt đầu bằng nhóm khác.
Dạ có.
Ok rồi, xin mời nhóm số 1.
Can you see my slide now?
Yes.
Okay. Hello everyone. Today I'm gonna present our project is Bitcoin price prediction. We are group on contain 5 members. Đỗ Quốc An, Hà Vũ Anh Đạt, Nguyễn Hoàng Đăng, Tạ Việt Cường, and Bùi Anh Đức. As you know, Bitcoin is cryptocurrency and a form of electronic cash. It is a digital currency that can be sent from user to user on the peer-to-peer Bitcoin networks. It keeps a record of trading among peers, and every record is encrypted. Each new record created contains the cryptography hash of a previous block. Each record contains a timestamp and the data of the sender, the receiver, and the amount. Given Bitcoin's image technology and few predictions are made on Bitcoin's future values. The crypto markets evaluate unpredictable and nonlinear markets. Accurate Bitcoin price prediction is extremely difficult, depending on many macro and micro factors, such as global economic context, unexpected shocks. However, all of the above also means that we have a lot of data to figure out the pattern of the Bitcoin chart. Therefore, we have found methods and techniques to detect trends and movement laws of the markets. In this project, we look at different deep learning networks and methods to improve accuracy, including min-max normalization and Adam optimizer. We have been collecting Bitcoin price data every 15 minutes, and we have rearranged them to reflect Bitcoin price from August 17, 2017 to present. We have taken 60 past low and high values as input, and the output is Bitcoin's next low and high price. However, predicting only one output value of 15 minutes won't have to suggest trading. So we have used 60 past value as input, and output is the next 10 values, enough to set up a trader sub-trading offer. We compared different models and found that the recurrent neural network short-term memories is not suitable for the case of price prediction based on the current trends. Long short-term memories provides the best relative prediction when the past memory is long-term memorized, and gated recurrent units are also used. However, the models are still unable to
Sorry to stop you. I just have a request that for every group before the presentation, you should upload the slide to the chat so that everybody can access the slide and ask question. And I will collect the question, the discussion from you guys, and will give bonus to the classmate that participate in the discussion with the group. So please, I encourage you guys to participate in the discussion, ask question, and whatever you want to clarify the idea for every group. Okay, so let's continue.
Okay. However, the models are still unable to accurately predict the price of Bitcoin at time of sudden price increase or decrease. The next part is dataset exploration. The Binance Exchange provides APIs to users once they have Binance accounts. We use that API and write a short Binance code to get the data from the website. Data is saved to the database, constantly updated and retrieved when needed. Bitcoin data from August 2017 to December 2021 is collected. It has timestamp the value as open, high, low, close, the volume traded in Bitcoin and USDT, the number of traders, and the date. This project focused on predicting future Bitcoin price using past price for trading, so only low, high values, and daytime I used. Next part is data processing. After collecting the data, we need to process them before training with the models. Little processing is required, replacing the NaN values with the zeros and previous data. However, our data had no location loss or corrupted. And to make the model conversion easier and faster, we use the min-max normalization to normalize the data from about the interval from 0 to 1. To forecast the price of Bitcoin, we will use the past value to predict the futures. The assumption of time series model is that the patterns are in the past. Candlestick pattern will be repeated in the futures. So usually we train the model on the past data, then shift the time frames to forecast the future. At each time step, we will shift the window frame by one time so that the past value of the white box is cast as the input variable and the current values of the blue box is cast as the target variable. Actually, the value of time step is 20 is just enough to form the rule such as a triangle pattern or the dozy pattern. Therefore, we use a time step equal to 16. Next part is a model for tạp biệt cường present.
Now we will present about the model we use in this project. First one is recurrent neural network. It is a group of methods to calculate product from the previous result of the model and new input data. In fact, it is better than MLP because it has equivalency from the last calculation that will influence its calculation. The equivalency gained from the model is kept private but allowed to pass to the next model. This private variable is called hidden state and is passed on from the current calculation to the future calculation. And then use memory to store information from previous processing to make accurate prediction for the current prediction. An model can be clearly described in this figure. The input actually will be combined with the hidden layer ht-1 using the SW function to calculate the current hidden layer ht and the output yt. The function sw is usually a time function. And then use three request metric for two computation. W combined with H t minus 1 and wx combined with ht to get ht. ht then combined with wxy to calculate yt. First of all, about recurrent neural network. Although it has some advantages over MLP, it still has limitations. An model cannot remember too fast for data with long-term dependency. Therefore, to reduce this phenomenon, we use long-term memory. In the T state of the model, we have input C, T minus 1, ST minus 1, and HT, where HT is input in the T state of the model. C, T minus 1, and ST minus 1 is the output of the previous state. Output CT and ST is called shell state and hidden state. In the graph, FT, IT, and OT are respectively forget gate, input gate, and output gate. Forget gate FT decide how much information to discuss from the previous state. Input gate IT determine how many input will affect the new state. Its output is in the range 0 to 1. So if IT equal to 0, it will ignore all information. And if equal to 1, it will keep all information. And output get OT determine how much information can go out and propagate to the next state. Here CT title is the same as ST in the ANN. If ST equal to 0 and IT equal to 1, we get a recurrent neural network. And CT is like a conveyor belt. Information that is important and either later is sent there and either when needed. So the information can be carried further. Now we talk about the guest recurrent unit. This is a variation of the long short-term memory model. Get recurrent unit is considered as one of the simple model when compared with LSTM model. A combination of the forget state with the input state into one, and as a result require only one hidden unit. Here is the formula of reset gate and update gate. In reset gate, we see that if RT is close to 0, and then we will not get the information of ST minus 1, and if it's close to 1, it becomes a recurrent neural network model. In update gate, If the value of zt equal to 1, then ht equal to ht minus 1. In this case, the information of ht will be ignored. Among the three methods, recurrent neural network can be very accurate given the fact that the model has a large training set. However, long-term patterns cannot be memorized, and this may result in inaccuracy, especially when rapid trends take place in recent years. LSTM can choose whether it should forget previous state. Therefore, it is better capable of dealing with data that has repeated trend and over a long time. Guess recurrent unit model is also able to choose whether it should recall the previous experience, but it is capable of learning more rapidly and need a bit fewer resources. In the previous session, we only discussed recurrent neural network, long short-term memory, and guess recurrent unit with only one unidirectional hidden layer. In many cases, the network will be we increase the number of hidden layers. Now talk about the model type. First, we use 60 input value to predict only one output value. Therefore, the model is many to one form. However, using the one output for 15 minutes will not be able to predict a lot of trading information. So we decide to use 60 value for the input, and the output is the next 10 low and high value. Therefore, the model is many to many form. Now we move to training and experiment section. First is dataset with 1,152,782 data points collected corresponding to the periods from 17 August 2017 to 31 December 2021. We use the last week data to evaluate the model. The rate of data will be 90% for training and 10% for validation. As the time series data symbols are not randomized, now we move to some evaluation methods. First part, we use some evaluation quantity. Root mean square error represents the difference between the actual value and predicted value. Extract by the square root of square the average difference over the dataset. Mean absolute error represents the difference between the actual and predicted value. Extract by average the absolute difference over the dataset. Mean absolute percentage error represents the average absolute percent error for each time period minus actual value divided by actual value. Here we denote N is the total intensity in the dataset, Y is the actual value, and Y hat is the predicted value of Y. Now, Đức will present another evaluation method, shading.
Okay, I'm going to present about shading. In addition, the familiar evaluation quantity such as root mean square error, mean absolute error, mean absolute percentage error. Then in this problem, we also use another way to evaluate whether the model is good or not by putting the model into prediction in reality for shading. We compile the training and validation set to retrain the model for the best prediction. We have created a virtual trading account on the Moon XPT exchange with an initial amount of $1,000. The model after training will be used to predict the next 10 high and low value. We will rely on the signal to place a buy or sell order. For each order, we use 10% of assets about $100 and leverage multiple 10 or multiple 20. We buy on the signal and the loss value calculate about to calculate the entry stop loss take profit value. For example, with the buy entry order equal to the lowest value of the signal, take profit is the highest value, and the stop loss is the difference between entry and MAE value. We check with risk divide reward ratio, which is greater than or equal to 1 divided to 1 risk is equivalent to the difference between entry and stop loss. So if the difference between take profit and entry must be greater than or equal to 2 times a risk, then we will place an order. Trading result will be recorded in a text file in the source code of this project. Next part is experiment result. In the first step, we try to set the predictive model with 60 input and only one output value. 5 models were used and evaluated on the validation dataset. And as you can see, one layer LSTM and one layer GIU have low coefficient. However, using only one output for 15 minutes will not be able to predict a lot of trading information, even though the result from the single layer model LSTM and GIU are quite good. So we decide to use 60 value for the input and the output is the next 10 low and high value. From the result of the model, when predict one value, we found that model using 2 or more LSTM layer proved to be less effective than simple model. After testing through several models, including more complex models such as encoder, decoder model, convolution LSTM, we obtained the best result in the following 3 models. Which is INN, GIU, and LSTM. After trading, INN have bad result with 2 profit order and 8 loss order lead to loss $35, while GIU and LSTM have quite good result. LSTM profit $32 and GIU profit $27. You can see the model phone to capture the past where the Bitcoin value drop. And next part is summary. According to the above research, one layer GRU have an evaluation value on loss function, but when put into price for trading, one layer LSTM proved to be supervised in terms of profit. Both model have close performance, so different model may be preferred in different situation. The GIU model requires less computing power, while it has slightly lower performance than the LSTM model. The LSTM model have so its long-term memory ability when trained with data that require long-term memory capacity of time step equal to 60. A semester is neither too long or too short. Therefore, we have not been able to test too many models for this problem. We can see that although both of the above two models are extremely simple model, if we use predict from them appropriately, we can still make a profit without using complex model. Although our model is yet to be able to learn Bitcoin's sudden price spike drop. Beyond this research, future work can be done on predict and estimate sequence so that it can be applied in more common Bitcoin transaction scenarios.
Okay.
Thank you for listening.
So, do we have any question from the class?
Question from Đặng Vũ Hoàng Hiệp. Are you sure the weekly profit will be as you test the Z model? I think I'm not sure because maybe the model will only be able to execute orders in a certain case or in certain price range. It really has to predict what the price will be. Anyway, I believe this model can be a pretty useful reference indicator for trader.
Oh, the question, I see that we have a comment from Nguyễn Văn Thanh Tùng. He said that the trading, I think that you guys should turn on the mic and discuss, right? It's not efficient too. That's why something on the text on the chat. So Nguyễn Văn Thanh Tùng said that he thinks the number of order is too small to evaluate the model efficiency. I think this comment is right. So you should test with the longer period. Nguyễn Hoàng Anh, can you speak? Nguyễn Hoàng Anh. Hello.
Yeah.
Yes. So let's discuss. Right.
Okay, so I have a question for your group. Can you guys recall how many parameters you in your model?
From question from Nguyễn Văn Thanh Tùng, I think I have a lot of order, but it only match with it with small though. Can we go how many parameters you in the model?
Oh, I have a question. About the order that you have matched. So this order have matched for how many, or in what period? I mean, from what time to from the what is the start time and what is the end time to take this order?
Start my order is placed in 10 in 10 candle.
No, I mean you check in what period of time from what is the start time? I mean the month, the exactly day that you check. So I think you have checked. You should apply this model in long period of time. So maybe the match order.
Can you speak my Vietnamese to clearly?
Ok, ý mình là với những cái order như thế, những cái model như thế này ấy, thì mình nên check trong cái khoảng thời gian rất là dài, ví dụ tầm 4 năm đi thì mình nghĩ là số lượng order nó phải lớn thì nó mới đảm bảo hiệu quả để đánh giá ấy. Và mình nghĩ là cái này là mình nghĩ một lời khuyên mình thôi là nếu mà đánh giá ấy, thì mình nên so sánh nó với cái việc mình check với lại mình hold. Ví dụ cái đồng đấy mà mình hold 4 năm thì so với mình chết nó có hiệu quả không?
Nghĩa là đang so sánh đánh giá giữa hold với lại chết xem cái nào hiệu quả hơn.
Mình nghĩ là cái phần này hồi trước thầy Trung cũng nói rồi là mình phải đánh giá giữa hai cái này ấy. Mà mình thấy nhóm bạn vẫn chưa làm, với lại trong cái giai đoạn cái phần đánh giá này ấy, mà số lượng order nó bé như thế kia thì nó khá là thiên vị cho từng cái cho từng cái model.
Ra là trong một tuần test ấy thì có rất nhiều lệnh được đặt, nhưng mà kiểu như là nó không khớp, cái giá mà đặt lệnh nó không khớp với lại cái giá thật đấy, nên là nó bị trượt nhiều lệnh, nên là chỉ khớp được những con vậy lệnh.
Thì mình là thay vì bạn dùng trong một tuần thì mình có thể dùng trong vài tháng hoặc là một giai đoạn 1 năm chẳng hạn, thì nó sẽ hiệu quả hơn.
Okay, nhưng mà tại là chết đến 15 phút cho nên là nếu mà 1 tháng hay là 1 năm thì thật sự cũng lâu đấy.
Nhưng mà vấn đề là trước khi em tiến hành paper test thì em phải tiến hành backtest trước, chứ backtest lúc đấy em đâu cần một cái môi trường trading thật đâu, đúng không? Em chỉ cần reserve một cái khoản dữ liệu mà ân xin ra để em test, em chạy trên đấy thôi, và em coi như là cái giá mà em mua ấy chính là cái giá mà thực tế là gì, là cái giá của cái điểm dữ liệu đấy, chứ không tính cái trường hợp mà cái giá em đưa ra nó không mua được. Trước mắt là em phải backtest, nó phải nó phải lãi đã thì sau đó em mới paper test được, đúng không? Đây em tự nhiên đi vào paper test luôn, có phải tự nhiên nó bỏ qua cái giai đoạn kia dẫn tới cái việc test của em nó kéo dài lâu đúng không? Nhưng mình thấy đây trong cái dữ liệu của em đây em có cái dataset em chia thành một cái đoạn từ tháng đấy từ tháng 7 đến tháng 11 à? Đến tháng 1 năm 2022 này. Cái đoạn màu cam này em không test à?
Ủa,
Em quay lại cái slide số bao nhiêu nhỉ? Không có số trang 16 ấy. Đây này. Thế cái đoạn màu cam này em không test được à?
Đoạn cam đấy là đoạn tập validation để em tính loss thôi ạ.
Đi tập test
Đấy
bé
là
quá. Thế ngay cả trên validation thì em có check xem là em mua bán nó có lãi không?
em chỉ test ở đoạn cuối thôi, còn đoạn này em chỉ tính để tính loss ra thôi ạ, để xong rồi để đoạn cuối này em chơi.
Ok rồi. Có ai có câu hỏi ra khác gì cho nhóm nữa không?
Nhưng mà thật ra đoạn cam đây nó cũng là vài tháng đấy ạ, cũng không phải ngắn lắm mà đến 15 phút.
Nhưng mà vấn đề là em không test trên đoạn đấy đúng không? Em không đo
Vâng.
xem ứng với cái giải thuật mà em đưa ra ấy đúng không? Thì nó mua bán thì có lãi hay lỗ và lãi lỗ bao nhiêu?
Tại là em trên tay ở trên cái tài khoản mà lập ra kia, cho nên là em chỉ chơi từ cái lúc quấy này thôi cả. Tại trước đấy thì nó đã lâu quá, cách đây vài tháng.
Không, mình bảo là em không cần nhất thiết là phải test với một cái môi trường trading thật, đúng không?
Vâng.
Em chỉ cần giả lập là ok, là tức là backtest là test trên dữ liệu quá khứ là được mà đúng không? Em không hiểu ý tưởng của em. Tức là
Em thấy kiểu, nhưng mà em kiểu viết code test ra thì em thấy nó kiểu hơi thiên vị ấy, bởi vì là kiểu nó...
vấn đề nhá, em hiểu không? Khi mà em đu cái backtest như này, tức là chạy trên dữ liệu quá khứ đúng không? Mà em chấp nhận cái vấn đề tức là cái giá thị trường đưa ra là giá em mua được đúng không?
Vâng.
Như vậy là nó dễ cho cái con bot đúng không? Đúng không?
Vâng. Vâng.
Trên cái môi trường paper test của em kia đúng không? Giá em đưa ra chưa chắc đã mua được. Tại vì khi em đưa
Vâng.
ra lệnh đấy có thể là nó đã nhảy cái giá khác rồi.
Vâng.
Đúng không?
Đúng
Nhưng
rồi.
mà hỏi mình đặt ra là trên cái môi trường backtest giả lập của em đấy dễ như thế thì không hiểu nó có lãi hay không. Mà tại nhau mà em lại bụp luôn em chạy ra paper test, có phải là khó không?
Dạ vâng.
Ok, có ai có câu hỏi nữa dành cho bạn không? Ok, nếu không thì mình cảm ơn nhóm và mình xin phép log lại các bạn của bạn cho mình.
Vâng. Em cảm ơn thầy.
Ai tham gia đặt câu hỏi cho nhóm nha. Trao đổi đặt câu hỏi cho nhóm. Alo. Alo.
Alo, thầy bảo không ạ?
Sao các em?
Thầy thầy vừa bảo là ai hỏi tiếp không hay là sao ạ?
Không, mình hỏi là ai tham gia trao đổi vừa rồi ấy, thì cho mình thông tin để mình log lại, mình ghi chép lại.
Em là Thanh Tùng ạ, em vừa có tham gia trao đổi.
Nguyễn Văn Thanh Tùng mà.
Dạ vâng.
Em có mấy câu hỏi dành cho nhóm ấy nhỉ?
Dạ em vừa nói về cái phần evaluation với lại bật mic nên nói thôi ạ.
Thế à? Ok rồi, còn ai nữa không?
Em là Hiệp ạ.
Gì Hiệp nhỉ? Lớp có một Hiệp thôi à?
Dạ em có hỏi về cái weekly profits in the test model.
Còn ai nữa không nhỉ? Ok rồi, thế xin mời nhóm tiếp theo. Trong nhóm 1 lúc đấy ai tham gia trao đổi nhỉ?
Em ạ, Bùi Đức ạ.
Còn ai nữa không? Một mình em cân cả nhóm à?
Lúc trả lời câu hỏi thì em trả lời, tại mấy câu hỏi này về cái phần trading nên là em trả lời.
Rồi ok, mình nói vui vậy thôi. Cảm ơn em.
Vâng.
Xin mời nhóm tiếp theo. Tiếp theo là nhóm nào? Các bạn thống nhất là nhóm nào đây?
Nhóm 5 bọn em xin thuyết trình ạ.
Nhóm 5. Ok rồi.
Thầy là các bạn sẽ nhìn thấy slide của bọn em chưa?
Mình thấy rồi em.
Okay. Okay. Hello guys. Welcome to our group presentation. This is the group 5, and our group topic is conditional image generation. And now I will introduce you about our group topic. After introduction, we will refer the method and architecture used in the
Sorry,
project.
stop you, but you have to send the slide to everybody before the presentation.
You mean we send the slide on the chat?
Yes.
Okay, wait a minute. Okay, can you see the slide I sent in the chat? Okay, let me continue about the content of our project. After introduction, we will refer about the method and architecture in the project. And after that, we will talk about the training process and model evaluation. And finally, we will conclude some idea about the result. And about the introduction, generative adversarial network, which can in short a deep neural network structure, and can have two parts, which is the generator and the discriminator. Because this part we have a study in our class lecture, so I will be quick. However, the GAN have some disadvantage. It cannot control the label that were generated, and therefore we have the C-GAN here to solve this problem. And by it solves the problem by embedding the wanted label in the input data, and a C-GAN here to solve the problem by adding an additional classifier at the end of the discriminator and learn both real and fake classification. However, both these approaches have some disadvantages. For example, it cannot take advantage of the data augmentation. This technique hinders the learning of GAN structure, while they cannot contribute to the learning of classifier. Moreover, the image generated by C-GAN and AC-GAN have also not obvious label, especially for the hard label. Therefore, we come up with the control GAN, which can solve the problem. The idea is to make a separate classifier from the discriminator, and now the discriminator job is to classify the fake and real data only, and the classifier will write the attribute of the generated data. Next is to the method and architecture.
Okay, so it is my turn to talk about methods and architecture. As we all know, this is the loss function that we use for vanilla GAN. It is based on the minimax game. The job of the discriminator is to maximize this function here, and the job of the generator is to minimize it. However, this loss has several problems, and one of them is unstable learning. For example, if we have a really good discriminator, but the generator is not good enough, then the whole thing here will be prone to be zero. And since the loss of the generator will be this part log of dgx, so then the gradient from the generator loss will be very big, and that makes the training become really unstable. So to combat that problem, a new loss function was introduced. It is called Wasserstein loss. Initially, Wasserstein loss contained only the first part, as you see here, the discriminator loss. It is declared based on the Wasserstein distance. It is to measure the similarity between two probability distribution. However, this loss is still not perfect because it has one condition, one constraint to satisfy. That is, the discriminator here has to be a function that satisfies the Lipschitz condition. And to enforce the update of the discriminator to preserve the Lipschitz constraint, we have a new part here called gradient penalty to ensure that the gradient of the discriminator will be less than or equal 1. And we have a penalty coefficient lambda to as the weight for the gradient penalty. So here, since we have 3 models, discriminator, generator, and classifier, we need to make the dual game become a 3-player game. The discriminator will minimize this whole loss function right here, and the generator will take both signal from the loss function and the signal from the classifier. And the classifier job is only to minimize its own loss, to classify the label correctly. And here we have some new parameters. C here denotes the classifier, lambda t here as the generator is a weight parameter to balance between the signal from the classifier and the discriminator. And okay, so next part. We introduce a new parameter E. It is the ratio between the loss of the real data and the fake data. And the idea behind E is that we want to, how to say, to decide that whether the training should focus on the label or the quality of the image in terms of realisticity. Okay, so another new parameter is gamma. It is to, oh no, it is to balance here, of course, to balance the loss from the classifier and the loss from the discriminator to the generator. And lambda here, gamma is actually a learnable parameter, and we update it through time. Okay, so next part, my partner will talk about architecture.
Hello everyone, Zen is our model architecture. We build our model including a generator, a discriminator, and a classifier as CNN models based on residual architecture. A major problem is vanishing gradients. So residual architecture may help us to solve the vanishing gradients. Yeah. And then here is the network architecture of classifier. We We use Recurrent as the activation function soon after the first linear layer, and sigmoid is the activation function of the last linear layer. But normalization is used in X residual block, and then in the network architecture of generator. As you can see, batch normalization is used in X residual block, and X residual block used to hidden convolution layer and recurrent for activation function. Here is the network architecture of discriminator. In discriminator, the layer normalization is used in X residual block, and X residual block used to hidden convolution layer and recurrent for activation function. And next part is training the model. Here, my partner will talk about the training the model.
Okay. Hello. In this start, we use the dataset whose name is Celeb A. It has 202,599 celebrity image with 40 attribute annotation of each one. There are two versions of image. That is image in white, and the second is image crop light and be resized to 178 multiplied by 218. About training detail, first we initialize parameter with Adam optimizer, set beta 1 equal to 0 and beta 2 equal to 0.9. It will have 160,000 iteration with 64 batch size, learning rate for generator, and discriminator part can vary for in this interval. The parameter E we use is 0.05, and learning rate R for gamma 0.01. With noise input vector is 500 dimensional vector from normal distribution. After initializing parameter, we pre-train classifier separately and fixes. About data pre-processing, we resize image to 128 multiplied by 128 and normalize them. The discriminator is trained for 5 iterations, then the generator is trained for 1 iteration. So hereafter, Zhang will evaluate the model.
Okay, so now we move on to the model evaluation part. To evaluate the conditional GAN model, we need to focus on 2 things. The first is evaluation the quality of generated image. Secondly, we focus on the label correctness. As we said before, the control GAN is designed to handle the detailed attributes, which is hard to be done in C-GAN and AC-GAN. But firstly, we will go through the smarter attributes. We generated image with label is male and female. As you can see on the slide, the generator worked correctly. It succeeds in clearly distinguishing in the major attribute. In this case, is gender label. Now we will check the model in hardware attributes. Okay, let's see in the run attributes. Now focus on the run 0 column. You can see that when the run is 0, it means the run attribute is deactive. And you can see that this guy is older than this guy. When the run is 1, that the run attribute is active. It also correct in speak low and speak clip. You can see that in the column big low is 0. Then the slow in this guy is pretty small, and when a big low is 1, that's this low this guy is bigger. Also we correct in the lip. You can see that. Not only our model not only can generate the image with half attributes, our model also have the ability to extrapolate zero-shot learning. Okay, so I think I will explain a bit about how we can encode the label attribute to generator. In training phase, we use binary encoding, 0 and 1. 1 when label is active and 0 when it's not active. In extrapolations, instead of just using 0 and 1, we try to use other values that the model doesn't see in the training phase. For example, we have here is -1, -2, and 2. Okay, now look at on the picture. You can see that in the run -2, this guy is even older than this guy, right? And about the big nose, when big nose is -1, then you can see that this guy have very small nose, and when big nose is equal to 2, the guy is very big nose. It also correct in the big lip. You can see that when the value of big lip increase, then the size of the lip also increase. This is now the example of extrapolations. But now we combine 2 attributes, and let's see how image look like. You can see here the smart attribute is corresponding to x-axis, and the attribute mouse slightly open is corresponding to the y-axis. In every column, you see in every column, when the value of mouse open slightly increase, you can see that the amount of this woman is bigger. In every row, when value of attribute smile increase, you can see that this woman is smile harder. So in conclusion, the idea is making separate classifier really improve the conditional generative model in terms of label correctness. Well, our control gun work pretty well, not only in handling the detail attribute, it still can do well in the label which is have a level train. However, there are still some issues in our model when you focus too much on extrapolation. Let's say if you set the value of attribute too high or too low, then we will lose the quality of the image. And technically, our generated image is still predictable by human, that is fake or real. So in the future, well, I think if we have to, such a powerful hardware, you can train the backbone. Let's say, we can do the backbone as the progressive growing gun to improve the generated image. And this on about our projects. Now we move to the Q&A sections. So, do anyone have a question for us?
I think that we should clarify between the conditional GAN and control label GAN. I think you mix up the concept in your slide. At some point in the beginning of the slide, you say control GAN, control label GAN. In the last slide of your presentation, you say it's conditional GAN.
Oh, I said conditional GAN. So it's maybe about. Maybe it's mistake. It's conditional GAN. So about the question from Tuấn, he asked that how long the training time take. This take us 2,000 hour, 3,000 hour, and we train in collab.
Okay, so I will answer the question from Chang. Did you use any score like FID or IS score to evaluate your images? Actually, we did, but the thing is, FID score and IS score, they are not universal evaluation for GANs, and I think GAN doesn't have a universal evaluation. I mean, unlike accuracy or F1 score, all FID score or IS score are not perfect. And since we train only one model and we don't have any baseline model to compare with, so I don't think we need to compare like mathematically. Okay, so like one he said that have you tried your own images? I'm curious about how they look. No, we haven't because we are too lazy to label our own face attributes. They have
Now
certain.
we'll answer the question from Søren. But the Søren asked us how we choose the vanity coefficient. So actually, the vanity coefficient we choose come from the Laptigan official paper. In the paper, they use the lambda equal to 10, so we just take it. And they say that in the practical, they do a lot of the lambda. And they see that when lambda equal to 10, in general, it's give us the good result. And about the question from Heinz, when training generator, how to compute lot in classifier parts. Okay, let me move
Okay,
to
so maybe I will answer this because I trained the classifier. So maybe my friend Tuấn forgot to say that when training the models, we train the classifier separately because the idea behind our model is we made the classifier separately from the discriminator. So we can train it, like pre-train it with several epochs before we train the generator and the discriminator. So the job of the classifier now is just a multi-label classifier, and we train it with binary cross-entropy loss as normal.
I think that you may re-explain again about the CGAN model because somehow I think the explanation is not clear enough for everybody.
Okay, so maybe I will take control and present again few slides.
Especially the way you train the model. I mean step by step. Maybe it would be more.
Okay.
Intuitive for everybody.
So first of all, we look at the GAN model, the top left, the most left model here. This is the vanilla GAN and don't have any consideration to the label, right? So to control the label, there are two methods that were introduced. The first basic one is CGAN or conditional GAN. Basically, we concat C here is the label. We take into account the label at the input of the generator and also the discriminator to control the label. But the problem here is the effect of the label. It just has effect on the input, and there is no signal from the loss function to control or to enhance the label part. And to solve that problem, another model, which is called AC GAN or auxiliary classifier GAN, was introduced, and now it have a classifier at the end of the discriminator here. And that classifier will have its own loss function. So in some way, the loss function, when it accounting the gradient, it will send back the signal to update the weight, right? And by that way, it can somehow enhance the quality of the label in the generated image. So that's better than CGAN, but the problem with a CGAN is the label is not obvious, especially for some detailed attributes. It's not obvious in the generated image. So here comes our model, which is basically make a classifier separately from the discriminator. So that's a new thing. And the advantage here is the classifier here can be quite deep, unlike the classifier at the ACGAN here. And classifier here, first it will give more precise control to the generated image in terms of label correctness. And also we can take advantages of data augmentation, which we cannot with these three models before. Okay, so about the training phase, first of all, since the classifier is now separate from other two models, we first train it separately outside of the training loop of the discriminator and the generator. So now, after training the classifier as a model for a multi-label classifier, we will come into the part where we train the discriminator and the generator as normal. First, we take a real image, and then we train the generator first. We take a fake image from the generator. We train the discriminator for 5 iteration with a real image and a fake image, and then we train the generator for 1 iteration. And the training phase of the discriminator and the generator is almost the same as for the vanilla GAN. Is that clear enough?
So what is the label here? The label here is the attribute of the face, right?
Yeah, that's right.
How do you force the modem to say that, okay, I want the face to have big smile, small smile, whatever?
Okay, so in the...
I want small smile, let's say, yes.
So a small smile, okay. So that has to do with the equilibrium parameter E here. So the idea behind E is that we want to measure the ratio between the classifier loss of the fake image in the denominator here and the real image in the denominator. Okay, but the thing is, we measure it on the test set, right? So theoretically, the denominator here is a constant, right? And so if we want to focus more on the label, or in other words, make the label become more obvious, or as you say, make smile become big smile, we will set E here to be small, close to 0.
I mean, but do you have the image saying that, okay, Z image is with big smile, Z image is with small smile?
Oh, okay. So, yes, that is on the test phase. At that time, we already trained the model, and as maybe my friend didn't explain good enough, so I will explain it again.
No, I'm
So
asking
when
face. I mean, if you have no label saying this is small smile and this is big smile, how
Let me
can...
answer the
so the label is binary encoded, so it will be a 40-dimensional vector with value of 0 and 1. 0 means no smile, and 1 means smile. There is no big smile.
For the training data, you have that information?
Yeah, we just have smile or not smile or something like that, not big smile. So it is one if the person is smiling, and it is 0 when the person is not smiling.
So can you show me the data set again?
Okay. The data set. No, I don't have it right now in my computer.
So the description of the data set, all right?
Oh, okay. Okay, so I will send it in the, yeah. You see it? Okay, so basically the data set has images and the label. Each image have 40 labels with binary encoded.
Yes, so that in the presentation you should verify that information.
Okay, sorry.
I think you're asking us about the CSV file, right? The label.
Okay, so in the meantime, I will answer some question in the comment section. Khánh asked when training the generator. Oh, I answered this question. So the question from Tùng, we use TensorBoard and we save the generated image for a fixed noise vector after every 100 iterations. So when the image looks good enough to us, we stop the training time. So we stop the training, just by eyeballing the image generated.
In addition, the question from Cho that because the GAN model is very tricky in evaluation, that you will not have something like the loss function. So say if loss function is close to some threshold that you stop the model, the GAN cannot do not have this. So we must do generate image in the TensorBoard and look at some image. If it look enough, and we stop the model.
Any other question?
Mình có thêm một câu hỏi. Bạn có thể slide thứ 5 được không? Slide này thì cái hàm lock ở phía sau này thì nó có cái lợi thế gì hơn so với cái lock ở tiếp tiếp này?
Ok, thì ở đây mình sẽ trả lời câu hỏi này. Thì nếu mà nhìn vào cái hàm loss ở trên ấy, thì trong thực tế người ta sẽ dùng cái hàm loss này để làm loss cho thằng discriminator, và loss của thằng generator sẽ là cái phần này, cái phần thứ hai. Nhưng mà đâu người thấy cái drawing chưa nhỉ? Thì trên thực tế lúc mà implement cái vanilla GAN thì loss của vanilla GAN sẽ là cái phần của thằng generator ấy, nó sẽ là cái phần này. Nhưng mà thay vì dx ở trong loss này thì nó sẽ là d của g ấy, tức là tính loss cho ảnh fake ấy. Thì vấn đề với thằng vanilla GAN loss này đó là khi mà thằng discriminator nó trở nên quá tốt so với thằng generator thì tức là cái phần loss này nó sẽ gần đến không, cái phần loss này nó sẽ cái phần ở trong ấy nó sẽ gần đến không, và khi đấy thì nếu mình tạo hào xuống thì cái không này nó sẽ thành một trên ở dưới mẫu thì cái variance trở nên quá to và cái update nó sẽ không ổn định. Và trong cái paper của Bani Aga ông tác giả cũng nói là cái đấy là cho update không ổn định lắm, thế nên mới sinh ra cái loss thứ hai này để giải quyết cái việc đấy và một số những vấn đề khác. Trả như thế là được chưa nhỉ?
Ok, cảm ơn bạn. Cảm ơn.
Any other question? Otherwise, we can. Okay, so who participate in the discussion? So please say your name.
Phạm Mạnh Tuấn ạ.
Nguyễn Vũ Thiên Trang ạ.
Phạm Mạnh Tuấn à?
Vâng.
Cho nhóm vừa rồi là nhóm số mấy nhỉ?
Nhóm 5 ạ.
5 này. Ai nữa nhỉ?
Em Nguyễn Đức Phú ạ.
Đức Tú á?
Đức Phú ạ.
Phú.
Em Nguyễn Quang Tùng ạ.
Công Tùng mà.
Quang Tùng ạ. Nguyễn Quang Tùng ạ.
Hải Sơn ạ. Lê Hải Sơn.
Quang Huy ạ.
Hải Sơn rồi còn ai nhỉ?
Quang Huy ạ. Lại Quang Huy ạ.
Trần Quốc Khánh ạ.
Nguyễn Vũ Thiên Trang ạ.
Còn ai nữa không? Còn ai nữa không?
Có người trong nhóm trả lời.
Người trong nhóm trả lời là ai nhỉ?
Lê Trường Giang ạ. Lê
Okay.
Trường Giang và ông Nguyễn Minh Châu ạ.
Như Thuần không?
Không, Lê Trường Giang và Nguyễn Minh Châu ạ.
Minh Châu à? Rồi còn ai nữa không nhỉ? Ok, chúng ta thể giải lao 5 phút nhé, sau đó chúng ta sẽ tiếp tục với nhóm tiếp theo. Alo, chúng ta tiếp tục nhé. Xin mời nhóm tiếp theo nào. Tiếp theo chúng ta sẽ đến với nhóm số mấy?
Thế đây nhóm 10 xin phép được trình bày ạ.
Ok.
Okay, so I'm here in group 10, and today our project, I will present about our project, image captioning. So our group contain 5 people. So first, I will talk about the problem description. So caption generation is a challenging artificial intelligence problem where the textual description must be generated from a given photograph. So as you can see on the right, we are given a photo, and the description must be generated. So this task require both methods from computer vision to understand the content of the image, and a language model from the field of the natural language processing to turn the understanding of the image into work in the right order. So you can see the example from the right. So about the dataset, in this project we are using a Flickr 8K dataset to build an image captioning model. This dataset contains one folder containing own image, and one text file contain raw caption from every image. As you can see the example, the first column is the ID of the caption, and the bị mất slide.
Sorry, who take control of our slide? Okay, I will share it again. Okay, no problem.
Okay, so the dataset contain one folder containing all image, and one text file contain raw caption of every image. As you can see in the example, the first column is the ID of the caption, and the second column is the caption of that image. Each image contain five caption. So with this dataset, we do some cleaning and pre-processing with the text. First is data cleaning. We clean the text by convert all the words to the lowercase and remove on punctuation to reduce the size of the vocabulary. So the reason why we have to minimize the vocabulary size because a smaller vocabulary will result a smaller model that will change faster. So after calculate, we having about 9,000 unique words across on the 40,000 image caption. So we decide to consider only those words which occur at least 10 times to contain in the vocabulary side, and after we cleaning and pre-processing, the processed work reduced to 1,651 word in the vocabulary. So next, we will talk about our model.
Okay, from this part, I will talk about how we handle the images and the text as input to our model. First, I will talk about feature extraction. As you know from CNN, we have a very popular, very famous CNN model called Inception V3. Inception V3 developed by Google Research, and its performance is very good because it was trained on a very large data set. So in this project, we will use this model for transfer learning. How can we use transfer learning by this model? Is that for every image, we for every image in our data set, we fed it into the model, and we remove the last layer, which is the soft mask layer, to get a bottleneck features as known as a fixed length vector. In particular, a 2048 length vector for every images. So as you can see from the diagram, um, the um, the architecture of Inception V3 is is like it's very huge, but we only use it for transfer learning. So this is for the feature extraction purpose only, or also known as feature automatic feature engineering. So that is for the um, converting the image into input of our model. Next, I will talk about how we treat the text to fed into our neural network. So for that, I will use word embeddings. Um, as you know from the natural language processing problems, word embeddings are very popular, and because it's a kind of representation that allow words with similar meaning to have a similar representation as vectors. So in this project, we use the GLOVE for word embedding, stand for global vector for word embedding. Um, and in particular, we use the 200 dimension long vector for each word. Um, um, so further, we will we will need to um, pre-process more of our data to make the model, to make the neural network understand our input. For that, we will need to add the tokens into our text data, or as our sentences. So for every sentence, we add the two tokens called start sequence and end sequence. Um, this we add this because it needs to like an attention for the model to kick off the generation, or to know where to end the generation, because our model only generated one word at a time, not all the sentence, not a sentence at a time. So we need to use that two tokens. And so for every unique word in the vocabulary that we have built from the previous part, we use an embedding matrix, which you know that each word will be represented by a 200 long vector. So all the vocabulary will become an embedding matrix um, to fit to model. So that is for the word embeddings and feature extraction. So next, I will talk about the one of the most important part of this problem is that how can we generate the sentence. Um, so at this to understand this, to make it more clear, we have to take an example. For example, image we given an image one, and the caption of it is the black cat sat on grass, but after token it became start sequence, the black cat sat on grass, end sequence. So as you can see, we have an image as an input and a caption, a full caption, a full sentence of a caption as a text input. But we will not want to fed all the sentence to the model at a time. So this is how we predict. First, we provide an image and the first word as input, and we try to predict the second word. And after predict the second word, we will provide the image again. I mean the feature extraction from of the image and the first two words, and we try to predict the third word, and then we input the first three words and we try to predict the fourth word, etc. And thus after after this process until it reach the end sequence, we will know that is the end of our sentence. And to be more clear, in this problem, so the last slide, the previous slide was to make you understand how the input is present in Word, but to be more particular, our model will not be use Word at the presentation. So to be exact, we will have to use the index to represent each word. So for every data point, we have a image feature vector and a partial caption, because we will employ a recurrent neural network RNN to read the caption. So a very important step to do is that we have to create, we have to make every sequence of caption to be equal length. That is why, as you can see, they are all zero padded in here. So in particularly in our project, we have calculated that the max length of a sentence is 34. So we will need to zero pad every partial caption to make it have all the length to be equal 34. So as you can see from the example on the right, all the partial caption must be padded with zeros at the end, and all the word turn to it turn into indexes. So next, I would talk about how we build our model. So first, we need to know our model is not like a straight model when that we will come from the beginning to an end. It's not something like that. And this is the model that takes two inputs, and we have only one input, one output as the next word that the model predicts. So we divide the model to three parts. The first part is to extract the feature and process the feature from photo. The second part is to process the sequence. To more exact, the partial caption is the sequence. And the last part is the decoder. So to be more to have a more to be exact, we have two input arrays, as I talked previously, that are photo features and encoded text at the embedding matrix, and only one output is the encoded next word in the text sequence. And something that we must notice here is that the output is not the word itself, or it's not something like an index of the next word, but it's one hot vector. Why is one hot vector? Because the model will predict, will have the output as a vector of probability, containing every probability, um, like the distribution of probability, and the word that the model predict will, at that position, will have the value of 1. So we can understand that will be a one hot vector output. Next, this is the diagram to make all of you understand and visualize the model. So let's begin on the right part, the right part. So as you can see, the input layer, we have, because we have transfer learning and extract a vector um, of every image. So on the input layer, we have a vector of 2048, and after a dropout layer to do the regularization, and after a fully connected layer, a dense layer, we have resized it to a 256 length vector. Okay, so the next part, I will talk about the left branch of the model. So something we must notice here is the input of the model is not the it's not the sentence, um, but it is the zero padded captions, and this caption should be go to the embedding layer, and this embedding layer will make it to be not trainable, because we use the embedding metric from the globe word embeddings. So the 34 length vector turn into 34 200 vector, and after a dropout layer and an LSTM model, this input also become an we also become a 256 length vector. So next, I will talk about how we merge the both two model. For the merge of the two model, we use an add layer. We add the two vector because it's equal in the size, so we can add them to be the output of 100 of the 256 vector, and we use a dense layer to process it, and we use a last layer to make it output to a softmax prediction. And as you can see, the output of the model is the vector of 100 and 1652, because that is the size of our vocabulary. So I hope it makes sense to all of you, because I have said that this is the probability distribution all over the vocabulary. So that's also explain why we on the first part we need to reduce the size of the vocabulary to make the model train more efficiently. So that is our my presentation about the model. Next, here we'll talk about how can we generate caption for the testing image.
Okay, so with our model, we do not generate a caption. with one single call to the neural network's predict function. Neural network's output is a fixed length tensor. So to get a variable length output, such as free from text, require multiple calls to the neural networks. So the neural networks accept two objects on which we map to the input neurons. First is the feature vector of the image, which is the vector with the length is 2048, and second is the ever-growing caption, which is a vector with the length is 34. So the caption begins with just the starting token, and the neural network's output is the prediction of the next word in the caption. The caption continues to grow until the neural network predicts an end token, which is the end sequence, or we reach the maximum length of a caption. Because we have calculated the vocab size of the training dataset is 1652. So the model will generate a 1652 long vector, which is a probability distribution across all the words in the vocab. So we greatly select the word which is the maximum probability. So the feature vector and the partial caption. This method is called MLE, which is maximum likelihood estimation. As we select that word which most likely according to the model for the given input. So we stop when one of two conditions met. That's encounter an end sequence, as I have said, token, which means the model thinks that this is the end of the caption, or we reach the maximum threshold, which is 34. So the model will stop generate. If any of above condition is met, we break the loop and report the generate caption as output of our model. So we having the caption for the image. So this is some example for the model prediction. So as you can see, the model run quite good. So to evaluate the model, we using loss and blow score to evaluate the model. So I will explain about the blow score. So blow score stands for the Pringle evaluation under study, which is a method of evaluating a translation based on reference translation. This blow score requires you have to have one or some sample sentence, and in this dataset we have a caption and some sample caption. So we can use blow score to evaluate, and blow score evaluates the sentence by matching it with sample sentence and give the scale from 0. Zero is absolute deviation to 1 is absolutely match. So blows is known as a simple method and easy to understand. So visualize blow. The calculation of blow is count the number of n-gram match between a sample sentence and the evaluate sentence, then divide by it by the number of tokens of evaluate sentence. So visually, the n larger, the smoother the sentence. So as you can see, we are having two phases of training and evaluate our model, and this is a result. So our conclusion. As you can see from two phases of training, the loss are reduced from 1.5325 to 2.3 to 2.3785, and this shows that the model is nearly converged to the minimal after some hyperparameter tunings. In here we are tuning the batch size and the learning rate at the second phase. The below score on the test set only improve a little bit, so we think this metric is difficulty to evaluate the model performance on our dataset, which so quite small. In the future work, we we do some future work and modification to make and improve our model. First is using a larger dataset, which we find is a COCO dataset. Is quite same with this dataset but larger. Second, we can change the encode model, trying different language models for web embeddings or using modern pre-trained CNN to encode the image. Or we can changing the model architecture, include an attention module. We also can do more hyperparameter tuning. In this project, we just do two phase because we're using Colab and the resource in the Colab is limited, so we just having time to do two phase of hyperparameter tuning. We can use the cross validation set to understand the overfitting and using dim search instead grid search in generation caption. So that's all about our project. Thanks for listening, and you can change for Q&A session.
Okay, so so I would like to understand clearly about the sequential network. I mean the way you feed the input to the network.
Okay, I
So at
this
some point I see that you have one subnetwork to encode the image, right? And then you have one LSTM to actually generate the sequence, right? Is that correct?
Yes, that's correct.
But at some point in the slide, I am seeing that you fed the input is a pair of image embedding and also the ongoing generated caption, right?
Yes, right.
So that was the input for the LSTM or something else.
As I said, from the part of caption generator, we continuously generate every partial caption, which you can see it grow after every iteration. So this partial caption is fed into the sequence model.
So you fed the image feature vector and also the partial caption to the LSTM.
Yes, and the caption is continuously growing until it reaches the end sequence.
I'm not sure I understand well about your point. Do you have the image? Do you have the image that describe the network architecture?
I think this diagram is all we have, but I think I can explain it more. So I will talk about in TensorFlow, we do have a method called fit generator. It's different from the fit method. The fit generator is that the model also consider a generator function, whereas it used the generator function as a way to generate an initial input as a very a number of every partial input. For example, a sentence like a sentence like this sentence, the black cat sat on grass. It will generate every partial caption like this. And when we fed the image and the start sequence, the model will try to predict the second word. And next, it will give the image, the feature image, and the partial caption of one more word added. And it will continuously doing that until it reach the end sequence. So
Okay, so
it's
this is the training data, right?
yes.
How about the testing phase?
On the testing phase, we cannot use the generator anymore. Because I have to explain that the model is it's not doing something like given an image and predict the whole sentence. It's not do anything like that. But given an image and a caption, or the caption of the only the partial caption, or maybe only one word, it will try to generate the next word. So we will use the maximum likelihood for example, we given a cat image, or maybe a cat is playing on the grass, maybe something like that. We'll fit the image of the cat to the model and the start sequence token, and it will try to predict the next word. And how we choose the next word is that we look at the the matrix, the 1652 music, which is the size of the vocabulary, and choose the 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 probability of the one which where it stands for the index of the word, and we will select it as the next word, and we will do the rest as choose.
Okay.
Yeah.
So this
And,
thing
and
is
and
somehow.
finally, it will encounter the end sequence token.
Okay, so I see. So it's that in the training phase you generate the data, right? And then in the testing phase you feed the token. I mean in the testing phase you do the inference as a normal LSTM inference, right?
Yes.
Okay, so any other question from the class?
So I will answer the question from Phan Đức Thắng. He asked that since the model is similar to an encoder and decoder architecture, have you considered using the attention mechanism? So I have considered using the attention mechanism, but I think I have a little try with it, but I have some difficulty understanding it. So I'm not included in my group project, but I also note it at the conclusion last slide that if we have to do some future work, we may change the model architecture a little bit and include the attention model. So Tạ Việt Cường have a very interesting question is that what if the model vocabulary doesn't exist, the object in the given image? So okay.
So okay, so I think
Hiệp can answer this question.
Okay, so I think I will answer the question of Cường. So what if in the model vocabularies doesn't exist the object in the given image? So when as you can see that we the first phase in data processing we resize and we minimize the vocabulary size, and if an object doesn't exist in the vocabulary, so our model will using the object and the word in the vocabulary to try to mm, have some present to the object which doesn't exist, and so this is an limit of our model. But when I think, but with the bigger data set and mm, in the future we can do with a bigger data set, and we try to exit a better model. So because the runtime of the model is quite important, so we just do a populate word to describe the many thing object, and it can be not accuracy, but it's a trade-off about the accuracy and the runtime. So because in this project we don't have so much time, so we if the object doesn't exist in the vocabulary model, we will try to describe it by the word in the vocabulary. So do you think that the answer is okay?
Okay, it quite clearly.
Yeah, okay, thank you.
Any other question? Okay, so if we have no questions, then I would like to have your name as you participate in the discussion. So please say your name.
Phan Đức Thắng ạ.
A moment, please. I need a few seconds. Anybody else?
Tạ Việt Cường.
Anybody else?
Người trả lời ở trong nhóm.
Ở trong nhóm, ok rồi.
Vâng, có Lại Quang Huy và Đặng Vũ Hoàng Hiệp ạ.
Okay. So we have just 15 minutes left. So I don't think that we have enough time for the next group. Group S, do you think how long does it take for you to finish the presentation? Because I have another course at 3. Boy. Okay, so let's continue with group 8. Bắt đầu đi em.
Vâng, thầy đợi em chút, em đang tải cái slide lên trên này. Ok. Thầy thấy slide của em chưa?
Thấy rồi em.
Okay. Hello everyone and welcome to our group's presentation. And the topic of our project is neural machine translation and various data augmentation techniques. And here are our group members. Our presentation will be divided into 4 parts. In the first part, we'll briefly go over the problem of machine translation and the need for data. The second part will explain the very popular and groundbreaking transformer architecture. And the last 2 parts will discuss the data augmentation techniques that we examine in this project, as well as their pros and cons. Machine translation, the task of machine translation is to translate a sentence or a document of a language to another, as seen in this example. And the most prominent technique to tackle this problem is neural machine translation, which models the translation as a sequence-to-sequence learning task. However, the effectiveness of this method relies on the quality and the size of the training corpus. And so with that in mind, we will examine 5 different data augmentation techniques, and experiments are carried out on the IW SLT 2015 English Vietnamese dataset using a transformer model. And now we'll talk about the transformer architecture. And overall, it consists of 4 main components: the positional encoding, encoder, decoder, and an output layer. So now we'll discuss the positional encoding layer. And since this model requires no recurrence and no convolution, the training phase and the inference phase is sped up quite a bit. And so to extract information regarding order of sequence, a position encoding layer is required. And in the original paper, the author uses an established function for this layer, as seen on the right-hand side of the slide. However, in this project, we use a learned position encoding instead, as this technique is used in modern pre-trained transformer such as BERT, Roberta, and VIT. Alo, thấy nghe thấy tiếng em không? Hình như là em vừa mất mạng, đúng không?
Có thể em.
Okay.
Nghe rồi kìa.
Okay. Each layer of the encoder consists of two sublayers, and these two sublayers are connected using a residual connection. And these two sublayers are multi-head, self-attention, and a feed-forward, linear feed-forward layer. Similar to the encoder, the decoder has n different layers, and each of these layers contain 3 sublayers, also with residual connection. These 3 sublayers are masked, multi-head, self-attention, multi-head attention, and a linear feed-forward layer. Okay, so what is this multi-head attention mechanism? And so the attention mechanism used in the multi-head attention is scaled dot product attention, which is very similar to the dot product attention proposed by Lung in 2015, except for the scaling factor 1 over square root of dk, with dk is the dimension of the key, I believe. Each word is projected into each key value query triplets, and these triplets are used to utilize multiple attention heads. So instead of only one attention head, we use each different heads. And later research shows that each of these attention head learns a different way in which words in the sentence correlate to each other. In this part, we'll discuss the data augmentation techniques that we use in this project. So the first data augmentation technique is synonym replacement. The idea is quite straightforward. Given a sentence, we randomly replace words with its synonyms. And for English sentences, it is very easy to do, as we have access to WordNet, which groups words into synonym sets. However, the meaning of a word can change based on its word type. And so in this example, we have 2 examples. In the first sentence, I fall down the stair. Fall is the verb. But in the second example, 3 leaves turn orange during fall. In this case, fall is a noun. And so we decide the synonym based on the word type of this word. And we use a POS tagging model to determine the word type. And for Vietnamese, as we don't have access to the Vietnamese variant of WordNet, we have to be more creative. And so, given a sentence, we replace the desired word with a mask token and pass it to forward. Yeah, as seen here. Forward is the Vietnamese variant of Roberta, and Roberta is a pre-trained transformer model. The pre-training objective of Roberta is one of the pre-training objectives is masked language modeling. And so we think that forward is suitable for this job, and we use forward to list possible candidates that we can use to replace the original word, as seen here. And we compare the cosine similarities of these candidates to the original word. Yeah, the second technique is back translation, and the idea is very simple. Instead of a English-Vietnamese transformer model, we trained a Vietnamese-English transformer model using the original data, and then we create a new data set by combining the EVN EVB news dataset and FPT open speech dataset to create a corpus consisting of 65,000 Vietnamese sentences, pass it to this Vietnamese English transformer to create English sentences. And we use these English sentences with the Vietnamese sentences to create new sentence pairs. The next approach is English-French back translation. The diagram of this approach is shown in the right-hand side of the slide. English sentences from the original dataset are fed to an English-French model to create French sentences, and then it is fed to a French-English model to create a new English sentence. And our hope is that this new English sentence retains the semantic meaning of the original sentence, but have a different surface form. The English-French and the French-English model we use are two pre-trained Marian transformer model developed by the NLP group at the University of Helsinki. And the Marian transformer model is just another variant of transformer, nothing really special. The fourth technique is construction. And the idea is that in English, we can construct words in a sentence to create a new sentence. As seen in this example, I do not know. We can contract it to I don't know. And constructing a sentence preserves the meaning. But expansion, meaning changing from the sentence of the right-hand side to the left-hand side, I don't know to I do not know. It may create misinterpretation, so we avoid doing so. So we do this using a dependency parser to check for the dependency tag of a nouns, which is used to help deciding whether to contract an auxiliary verb. And for contracting the not word, we only use regular expression. And the last technique we'll discuss is paraphrase generation. And the idea is that given an English-Vietnamese pair, we generate 3 paraphrases of the English sentence using a fine-tuned Pegasus model. And the paraphrase with the lowest blue score will be chosen. And we choose paraphrase with the lowest blue score to make a trade-off between surface form similarity and semantic meaning. So we sacrifice the semantic meaning for a more diverse sentence. And Pegasus is a pre-trained transformer whose training objective is abstractive summarization task. The task of abstractive summarization may require the model to generate novel words that do not occur in the original document. And so we think that Pegasus is suitable for paraphrase generation. Okay. And now are the experimental results. As stated before, the dataset we used to carry out experiments is the IWSLT 2015 dataset. And here are the statistics of the dataset. For each technique, we generate 65,000 sentence pairs, which is roughly 50% of the original dataset. And we trained a transformer model with 10 epoch to evaluate the effectiveness of the augmentation techniques. And here are the results. Here are the blue score of these, of the model. And so as we can see here, all 5 data augmentation techniques do make an improvement. And the best performing technique is English-French back translation. The worst performing techniques are back translation and paraphrase generation. And also the contractions method wasn't able to generate enough sentence pairs, wasn't able to generate 65,000 pairs. And now I'll talk about the pros and cons of each of these techniques. And so the first technique, the synonym replacement technique, it only requires monolingual data and can be used for both high and low resource languages. But however, this technique may occasionally create semantic changes, and sometimes the augmented pairs does not sound natural. And in this, the second technique, back translation, can utilize huge monolingual English dataset such as C4 or Huge News, which consists of thousands of gigabytes of text. However, the drawback is that the translation quality depends on the original data. And so, as seen in this table, the performance of this technique wasn't very good, wasn't excellent. And we suspect it is because the original dataset wasn't large enough and isn't large enough, and it contains noise in the original dataset as well. The third technique, English-French back translation, was the best performing technique, and it can utilize great open source pre-trained translation model. However, the drawback is that it has the longest augmentation time, and good pre-trained model might not be available for low resource languages. So, for example, in this case, our task is English-Vietnamese translation, and English is a high resource language, so there was available good pre-trained model were available for us. But for example, if our task is to translate from Vietnamese to Thai, and then both of these languages are considered low resource, and so good pre-trained models might not be available. The fourth technique, contractions, has the fastest augmentation time, and also the meaning of the sentence is preserved. However, it has limited augmentation capacity. And as seen in this table, it wasn't able to generate enough pairs. And also, there is no diversity in the augmented sentences. And it also works on English. And the last technique, the paraphrase generation, the pros is that there is a wide variety of grammatical structures in the generated sentence pairs. However, a fine-tuned Pegasus or any fine-tuned transformer for paraphrase generation is quite hard to combine and quite hard to produce as well. And so as we can find on the Hugging Face website, there's only one model that we think capable of generating good paraphrase. And that's it for our presentation, and thank you for listening.
Okay, so do we have any question for the group? Any question?
You use the transcript of FPT open speech dataset, which is designed. I think there is no domain mismatch because both the FPT open speech dataset and our original dataset are transcripts of speech. Our original dataset is the transcript of TED Talks, I believe. So I think there's no domain mismatch between these two data. Phạm Văn Cường asked, you use pre-trained models for English, French translation. Why not use one in case of Vietnamese English? Will it be bad for something? So the idea of our technique is to train it from scratch. So we cannot use pre-trained models in this case. Hoàng Văn Khánh asked, did you just take the best candidate or did you select a threshold on the consign score to take the top K best candidates? Viet, can you answer this question?
Yes. Can you hear me? Can you hear me well? Hello?
Yeah, we can hear you.
Okay. So you take the best candidate or you select the threshold. So we only use the best candidate as a replacement of the original word because from our observation, the word with the highest score is the most likely to be the synonym of the original word. So we just use the best candidate. I hope that answers the question.
Okay, so I think that I have no question for the group. Thank you very much for your work, and we will see each other again in the next week. See you. Bye bye. Alo, xin lỗi, mình quên chưa lấy thông tin của các bạn tham gia trong trao đổi vừa rồi ấy. Các bạn cho mình xin thông tin với. Alo, mọi người còn đấy nhỉ?
Dạ đấy. Có bạn Phạm Việt Thành, Phạm Văn Cường, Hoàng Văn Khánh, Vũ Quốc Việt, Phùng Quốc Việt, và một câu trả lời của em là lấy từ bạn Nguyễn Tuấn Dũng.
Em đọc lại cho mình Việt Thành này, ai nữa nhỉ?
Việt Thành, Văn Cường, Hoàng Văn Khánh.
Văn Cường này, Văn Khánh này. Còn ai nữa nhỉ?
Vũ Quốc Việt, Phùng Quốc Việt và Nguyễn Tuấn Dũng.
Vũ Quốc Việt á?
Là em.
Nhưng mà đấy là em tham gia trao đổi đúng không?
Vâng, nghĩa là lúc nãy em cũng có trả lời câu hỏi.
Vũ Quốc Việt này, ai là Phùng Quốc Việt đúng không?
Vâng. Và Nguyễn Tuấn Dũng ạ.
Ok rồi. Ok, chào cả lớp nhé. Mình phải chuyển qua lớp thứ hai. Ok, chào các em.
Vâng, em chào thầy.